We have a basis for our vector space, but it's a bad basis. The vectors are skewed and they aren't unit length. And any calculation we do with this toolkit is going to be inefficient and numerically unstable. What if there was an algorithm, a simple step-by-step process that could take this messy, contaminated toolkit and systematically clean it into a perfect 90-degree orthonormal one? There is, and it's called Gram-Schmidt Process. Welcome to Decoding Complexities. I'm Pradeep. The intuition behind Gram-Schmidt is to build a clean orthogonal basis one vector at a time. We call our new clean vectors u1 and u2. The first step is easy. We have nothing to clean yet. So we just accept the first vector as it is. This is our foundation. Now, for the second vector v2, we need to purify it. Right now, v2 is contaminated with a part that points in the same direction as our first clean vector u1. We can think of v2 as being made of two pieces. One, the contaminated part, the piece of v2 that is aligned with u1. And the second, the pure part, the piece of v2 that is completely new and orthogonal to u1. Our entire goal is to isolate that pure part. And how do we find the piece of one vector that's aligned with another? We use the tool we just mastered in our last video, the orthogonal projection. This projection is the bad part of v2. It's the contamination. To get our second pure vector u2, we just take the original v2 and surgically remove it. Let's formalize this. We have our starting basis, say v1, v2. And the step 1 is get the first clean vector. This is trivial. And the step 2 is get the second clean vector. We start with v2 and subtract the contamination, which is the projection of v2 onto u1. And we know the formula for that projection from our last video, which is u2 equals v2 minus the dot product of v2 and u1 divided by the dot product of u1 with itself. And that's it. We now have a new basis u1, u2, where the two vectors are perfectly orthogonal. And step 3 is to normalize these vectors to get the gold standard, to turn our clean orthogonal basis into a perfect orthonormal basis. We just divide each new vector by its own length. And this process extends to any number of dimensions. To find the third vector u3, we just take v3 and subtract its projections onto both u1 and u2. It's a simple, recursive, and incredibly powerful idea. So, why is this algorithm so important for engineers and data scientists? Because the Gram-Schmidt process is the mathematical engine behind one of the most fundamental operations in numerical computing, the QR decomposition. Think of it like compiling code. We start with matrix A, whose columns are our messy linearly independent vectors. QR decomposition compiles this matrix into two new highly useful matrices. The Q matrix is a beautiful orthonormal matrix. Its columns are the clean, perfect basis vectors, E1, E2, and so on. And we just built using Gram-Schmidt. And R matrix is an upper triangular matrix that records how the original vectors were combined to create the new ones. This process of turning any full rank matrix A into an orthonormal Q is critical for solving linear systems and is a cornerstone of many machine learning algorithms. Let's see this in Python. First, we will implement the process manually exactly as we derived it. We define two vectors v1 and v2. And the step 1 is to initialize the u1 with v1, and the step 2 is to calculate the projection of v2 onto u1 and subtract it from the vector v2. But in the real world, we would never do this by hand. NumPy has the entire QR decomposition process built into one powerful function. It is the linear algebra QR function. This single command performs the entire Gram-Schmidt process and normalization for us, giving us the perfect orthonormal matrix Q. So, We started with a messy skewed basis and used the powerful tool of orthogonal projections to systematically purify our vectors one by one. This elegant algorithm, the Gram-Schmidt process, allows us to construct a perfect orthonormal toolkit for any vector space. We are now masters of building and defining perfect coordinate systems. But this leads to a fascinating new question. We have spent the last 3 videos learning how to build and use this perfect 90-degree world of orthonormal vectors. This is the ideal world where our math is simple and clean. But what happens when the real world doesn't cooperate? What happens when our real world data points do not perfectly fit into our clean mathematical model? What do we do with the messy error that's left over? It turns out that understanding this error is the key. By finding the projection that minimizes this error, we can find the best possible fit for our data, even when a perfect fit is impossible. If this deep dive was valuable, hit that like button and be sure to subscribe, because in our next video, we will use the tool of projections to solve the best fit problem. And in doing so, we will decode the fundamental math behind linear regression. Thank you for watching, and I will see you in the next one.